Okay, so I'm going to try this. This admittedly is the fourth time that I've recorded this in addition to the Teams meeting yesterday. Unfortunately, this whole thing is testing my technical abilities. But I found this figure in the book, and this right here shows the cardiac cycle or the heart cycle. And I mean, it's pretty simple. We all know this. The sinoatrial node initiates a heartbeat right here. These are the depolarizing cells, if you remember, that we talked about, that really gets at what I would call the physiology of the heart. This is more macro physiology. It's more I don't know what it goes into anatomy even, but the physiology of the heart. What we have here is the threshold of the pacemaker cells, and you have these funny current channels, IF channels, and sodium's leaking in right here. So they're just really leaky to sodium. Let's redraw that. Sorry. Sodium, Na+. So that's sodium leaking in here, and then they reach threshold, and calcium really starts to pour in. So this is calcium through CAV, or voltage-gated calcium channels, and the voltage at which they open is right here. Now you go up, potassium starts to flow out of the cell, which is almost always the negative stimulus in a cell, and then you get back down here, voltage-gated calcium channels close, potassium reaches equilibrium. This is, if I remember correctly, about -90, and I think this is about -60. So remember, there's no resting potential per se. It just kind of goes down, and I can change the color back here if that helps. And then sodium starts to leak in slowly, and the duration of this determines heart rate. If it's really quick, if it's really slow. And this is modulated by beta and M2 receptors, and that has to do with those leaky channels, which are cyclic nucleotide gated. Beta receptors increase the concentration of cyclic nucleotides, CAMP specifically, in the cell, whereas muscarinic 2 or M2 receptors decrease the intracellular concentration of CAMP. The M2 receptors also phosphorylate the potassium channels, and what that does is makes the cells more leaky to potassium, which further lengthens this little interval here where calcium isn't flowing into the cell. So that's where we start right here with the sinoatrial node, and you can see what that does is there's little fibers coming out of the sinoatrial node that innervate the atrial cells, which are contractile cardiac myocytes. Okay, so the atrium contracts first. That signal goes through the intranodal fibers. Those intranodal fibers then reach the atrioventricular node. The atrioventricular node pauses for a few milliseconds and then sends that signal down the bundle of His. And what you can see here is when the sinoatrial node fires, causing the atrium to flex, you get a P wave. That P wave starts, and then the P wave's finished by the time you get to the atrioventricular node, because remember, as we talked about yesterday in class, the P wave is a electrical representation that you can detect in the body, and this is how an ECG is usually hooked up. If we were in lab, we would have done this. An ECG is hooked up. You put an electrode here, and then a grounding electrode here, and that's the minimal setup, you can have a 5 electrode, a 12 electrode ECG and get much more accurate, much more precise measurements that go beyond the PQRST wave. But all you need to get the PQRST wave, which measures the electrical activity of the heart, or an electrocardiograph. You might also hear it EKG. Remember, that's because the Germans were doing science, and but we've anglified it to ECG. So ECG is the preferred term. So there's the P wave. Then the signal travels down through these little wires that go through the septum, and then to the Purkinje fibers, which are right here. Those Purkinje fibers then trace back up into the ventricle, and the Purkinje fibers distribute this depolarization to all of the cardiac myocytes. Once you get there, you get the Q wave, which is the beginning of this ventricular depolarization. The R wave, which is the massive ventricular depolarization. A couple milliseconds later, the ventricle flexes or contracts, squeezing the blood out. And as it squeezes the blood out, the semilunar valve right here opens. This is the bicuspid valve, also called the atrioventricular valve. And that's just the generic term for both the tricuspid and the bicuspid valve. This is the semilunar valve. You also have a semilunar valve going into the pulmonary artery. You could call this the pulmonary valve and the aortic valve, to be more specific. So the two semilunar valves, and you'll hear me refer to semilunar valve multiple times. The two semilunar valves are the aortic valve and the pulmonary valve. The two atrioventricular valves are the bicuspid and the tricuspid valve. So that's the QRS wave right here. So the QRS wave is the ventricular contraction. Once that stops, you get a relaxation and a ventricular repolarization. This corresponds to, if we look at the, remember, this is the pacemaker cell. You can also look at the contractile cardiomyocyte. Let's not make it quite that big. Now this is the action potential, remember. You have sodium, potassium, and then you get a calcium influx that prolongs this plateau, or makes a plateau really, and then you have potassium again. This electrical activity, this depolarization, and this repolarization is what you're detecting, and it's just in mass or all mass. The all of the cardiomyocytes are doing this, and this is what you're measuring right here with the PQRST wave. The T wave is the repolarization. This right here corresponds to the T wave. So that is the repolarization. This is the depolarization, that R. So it's this right here that corresponds to the R wave. Now I've made a mess. So that's what the ECG is. And if we look at the ECG in regards to the rest of the the rest of the characteristics of the heart, we'll see up here. Here's your PQRST wave. Goes from here out to there. You can see down here, this is pressure in the atrium. At the P wave, what happens? Sinoatrial node fires, and the atrium contracts. Atrial pressure starts to increase, which makes sense. It's like squeezing a balloon. You're squeezing that balloon, the atrial pressure goes up and then comes back down, because what happens is you're squeezing it, and as you start to squeeze it, the pressure goes up, and then blood starts to flow from the atrium into the ventricle, and more blood leaves the atrium. Right here at this arrow, the atrioventricular valve opens. Right here, the atrioventricular valve closes, and it closes for a number of reasons. The contraction of the atrium is over, but also you see the QRS wave right here. The contraction of the ventricle initiates, and once the ventricle starts squeezing, the first thing it does is puts pressure on that atrioventricular valve and slams it shut. That's what this is right here. This is what you call an echocardiogram, not an electrocardiogram, an echocardiogram. This is just the sound of the heart. When the atrioventricular valve closes, you hear the first boom of a heart. You know, heart goes boom, 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 boom. This is the first one. We call that the lub of the heart. So that's the lub. This out here we'll talk about in a moment is the dub. So lub dub, lub dub, lub dub. And we'll talk about the timing of those, which is kind of interesting. But from the time the atrioventricular valve closes until this line right here, what you have is called a isovolumetric. They say isovolumic, but people say isovolumetric contraction. And iso means the same, volumetric or volume means volume. So the volume of the ventricle doesn't change from this line to this line. And that's because here the AV valve closes, and it's not until you get here that the semilunar or the aortic valve opens. You know, so that doesn't make a sound. A valve opening doesn't make a sound at all. But right here, what you're doing is you're increasing the pressure of the ventricle until it overcomes the back pressure from the artery. And the artery is a hose, and it's elastic, so it stretches out. So there's back pressure there. So nothing's going to come out of that hose nothing's going to come out of that valve until the pressure in the ventricle overcomes the pressure in the hose. The hose being the aorta. And you'll see right here at this point, that's where the ventricular pressure is greater than the aortic pressure. And that equals the aortic or semilunar valve opening. And what happens when the semilunar valve opens? Aortic pressure goes way up because you have all this blood flowing into it. The ventricular pressure keeps on going up even though blood's escaping because the ventricle is still squeezing down. There's still lots of pressure in the ventricle, and it goes up to this magical number, 120. If you're hypertensive, and there are many different reasons to be hypertensive, we'll talk about that in the next couple of lectures, it's going to be higher than 120. But regular, typical blood pressure for a human is 120 millimeters of mercury. At its peak, this is called systolic blood pressure. And the systole means when the ventricle is contracting. The converse or the opposite of that, the diastole, is when the ventricle is relaxing. So you have diastolic blood pressure, which is all the way down here. And you have systolic blood pressure, which is as high as it can get. You could also say systolic is right here. This is pretty equivalent all the way around, but it goes down to about 80. Okay, where are we? Okay, so here the blood comes out of the ventricle starts to relax. You can see from the PQRST wave, the ventricle starts to relax. This is the signal of relaxation right here. That contraction lasts, where's our little time scale? That contraction lasts about 200 milliseconds. So let's go to 200 milliseconds out. That's 200 milliseconds. That's about the time it starts to relax. Now, as your heart rate increases, all of these times can decrease a bit, but this is in a nice, resting, relaxing heart. So it's about 200 milliseconds from the initiation of contraction until the relaxation. As the ventricle relaxes, pressure starts to drop. You can see that red line is ventricular pressure. Aortic pressure starts to disperse because the blood is going from the aorta to the brachiocephalic, subclavian, and common carotid, then on down to the celiac and the abdominal aorta, the celiac, the mesenterics, all of the different arteries that it goes out. Go back and review the anatomy. And what happens is the aortic pressure now falls, now surpasses the ventricular pressure, because the ventricle is really relaxing and there's some blood flow back toward the semilunar valve, because the aorta is under a pretty high amount of pressure. It's stretched out and it's pushing blood. It's dropping, but the ventricular pressure is dropping even faster. So what happens, I'll draw this in green, and what I'm doing is following this black line right here. Aortic pressure drops, and right here, the semilunar valve closes. That's what this dub is, right? So as soon as that semilunar valve closes, blood is not flowing back toward the ventricle or back through the semilunar valve into the ventricle at all. As soon as it starts to flow back, as soon as the aortic pressure surpasses the ventricular pressure, that valve's going to close, and all that blood has to start going out toward the brachiocephalic, toward the abdominal aorta. And you see an increase in pressure because you cut off the escape valve. It can't get back into the ventricle. And this is called the dicrotic notch. That's that transient increase in aortic blood pressure. Blood flows through the blood system, and as it does, aortic pressure keeps on going down. Then you get back to here, and you get another flexion of the ventricle. Aortic pressure starts to go up once blood enters, goes up to a point, the ventricle starts relaxing, semilunar valve closes, aortic pressure goes back up. Over and over again. And this happens every second, right? So if we look at the atrial pressure, it increases because of the P wave, because of a contraction.
Who are you talking to?
The computer. I'm just recording a lecture, bud. Then the atrioventricular valve closes, same exact thing. The blood can't flow out anymore, so you get this little increase in pressure.
Wait, did you draw all that?
I did, buddy.
That's a long time.
I know it is. And then it starts to drop ventricular pressure increases. Atrial pressure doesn't care about ventricular pressure, but what's happening here is that you have venous return of blood into the atrium, so it goes up and up and up and up and up, drops off, comes back up once the atrium starts to contract again, and you get another atrial contraction. This is actually called, and this is kind of interesting, buddy, this is atrial systole. And this is atrial diastole. But it is not consequential in the arteries, so we don't really talk about that as diastole and systole. If we look at the volume of the ventricles, this is the volume
Did you
of
draw
the...
that?
No, I didn't draw that. I just drew the words. So the volume of the ventricles increases a bit here.
It'd be
This
cool
is when
if you draw
it would be,
those.
wouldn't it? If so when the atrium flexes, it pushes blood into the ventricle. That's why this goes up. Then you have your isovolumetric contraction. This is where all of the valves are closed. So nothing can come in and nothing can go out. Then you have an emptying into the aorta. This is where aortic pressure is increasing because the volume of your ventricle is decreasing. Then you have an isovolumetric relaxation. This is, again, when all of the valves are closed, and you can see right here, the semilunar valve closes. Right here at F, the bicuspid or AV valve opens back up, and that allows, by gravity, not by pumping, because the atrium doesn't flex until here. It doesn't contract until here. So all of this is passive filling by gravity of the ventricle. What are we having for lunch, buddy?
I don't know.
You don't know. What should we have
That's
for lunch?
what the letter that Evan's name starts with.
What letter is that? What do you call that letter?
E.
E. Good job. Okay. Okay, so this entire diagram right here, buddy, this is called the Wiggers diagram.
Wiggers?
Wiggers diagram, exactly.
Do you have a wig in your body?
It's like a wig you put on your head, isn't it? So, it shows the electrical activity right here. It shows the pressure, and it shows the ventricular volume. And all of these are tightly related, right? And remember, this is all based on those cells with the funny current channels that depolarize slowly. And then you have voltage-gated calcium channels that cause a massive depolarization of the cell. And then voltage-gated potassium channels that return it back down to about negative 90. And then you have those leaky sodium channels, those IF channels. And that spreads a depolarization event throughout the heart, causing the contractile cells, which I'll draw in another color of orange. How about like that? Does that sound good?
I don't know.
Why don't you know, buddy? That looks more like this. Oops, I'm doing that way too early. Be right about here. Boop. There we go. So that's the contractile cell mapped on top of the pacemaker cell. Isn't that neat?
Yeah, but I don't really know how it
Yeah,
does it.
I don't know if anybody really does.
Um,
Okay.